Hello, welcome to Basics of Finite Element Analysis. Yesterday we had concluded our discussion on weighted residual methods, and in the discussion on weighted residual methods and also which we saw earlier in the last week on Rayleigh-Ritz methods, we found that the trick in getting a good solution lies in making a good guess of what the approximation function should be like. And the requirement for choosing the right approximation function we had discussed was that it should meet all the essential boundary conditions in case of Rayleigh-Ritz method, and it should meet all the natural as well as essential boundary conditions in case of weighted residual methods. And it is not always easy to make these guesses. Now, in context of the problems which we have solved, these are relatively simple problems, one dimensional problems, but if problem becomes two dimensional and the domain is not just a nice rectangular square or a circle, but if it is a complicated two dimensional shape, then making such choices becomes extremely difficult. So, because of that, so that is one thing, and the second thing is that there is no standard method of making these choices. First thing is we have to make a guess, and also in this guesswork there is no standard approach or something like that. So, most of the real life problems remain unsolved because in terms of if we have to use these methods to find solutions for most of the real life problems. So, with that context in mind, people have developed the finite element method, and in context of finite element method, a couple of weeks back we had said that the process of developing a finite element method starts with, first you discretize the whole domain into small elements. Second, you take approximation functions which represent the displacement or the unknown dependent variable, how it varies over the element, and then use either the residue or the weighted weakened residue and you equate it to 0 over the element, and as a consequence you get element level equations, and then as a follow up you assemble these element level equations to get the overall assembly level equations. At that stage we apply the boundary conditions and we solve for the dependent variable. Today's class and next several lectures we will start this process and we will start understanding how the this finite element method works at a detailed level. And what we are going to do is that we are going to start in this direction by addressing second order boundary value problems. Second order boundary value problems, and the problems which we will deal will be linear in nature. So, one example of this boundary value problem, and this is what we are going to solve for, is a problem represented by this differential equation. So, this is the differential equation and it is valid for which is between 0 and L. So, our domain is 0 to L. In one of our earlier lectures we had explained that this particular problem, this particular differential equation, it represents a large number of classes of problems, starting from tension in a hanging string, electrostatics, bar under compression, one dimensional heat conduction, diffusion in one dimension, and so on and so forth. So, this is the problem we will learn FEA on as a first example. And what we will do is that the first step we will do is we will generate the weak form of this equation. Okay. And in this case, we will generate the weak form on an element by element basis. So, we are not going to generate the weak form for the whole domain. We will create a weak form which will be applicable to a small element. So, suppose this is my entire domain, x is equal to 0 to x is equal to L. I will break this up into small elements, and for the eth element I will write down the weak form. Okay. For the eth element I am going to write down the weak form. So, my domain is not 0 to L in this case, but rather it is from xa to xb, where xa is the first coordinate of the eth element, xb is the second coordinate of the eth element, and w is the weight function a du over dx plus c u w, I integrate it, and this equals integral from xa to xb q of q times w times dx plus w a du over dx to xb. The other thing we will add here is that this is the governing differential equation, and I will say that I know the boundary conditions for this problem, and the boundary conditions are that at u at 0 is equal to u0 and the value of a du over dx at x is equal to L is equal to some number q naught. Okay. So, these are the boundary conditions. Okay. So, this term I will expand it. So, this is my xa to xb. I am just rewriting the the right hand side of this equation again, and then I have a term w which is evaluated at location xb times qb, which is the value of a du over dx evaluated at x is equal to b, and here note this, the other term also has a positive sign, and I will explain that in a moment, and that is w evaluated at xa times qa. And the reason I am going to put a positive sign here is because I am defining qb as a du over dx at xb, and I am defining qa as minus of a du over dx xa. If I had not defined it with this minus sign, then this positive sign would have been replaced by a negative sign. Okay. So, this is something important to note, because what it does is it keeps our bookkeeping a little easier, that is all. The other point to note here is that the domain here is not the length, the overall length which is 0 to L, but it is the domain of integral is the length of an element. So, if there are 20 elements in the domain, then I will write 20 different equations like these. The next step, so what have I done? I have started with a differential equation. I have discretized my system into different elements, right. That is the first step which I did. I broke it up into all the elements. Then for each element I have written the weak form. For each element I have written the weak form. The next step is that for each element I will assume, next step, for each element I have to do what? Develop approximation functions. Develop approximation functions for u of x. Okay. If it is a linear element, the element has two nodes, then I will develop two approximation functions. If it is a cubic element, u is going to vary. If it is a quadratic element, u is going to vary in a quadratic way over the length of the element, and in that case I will have three nodes on the element. If it is a cubic element, u will vary cubically over the length of element, and I will have four nodes. So, what we are going to develop is an approximation function for a linear element for illustration purpose. Then we will generalize it for other situations also. So, for linear element, okay, I have two nodes and u x varies linearly over element. So, and then because it is there are two nodes, I need two approximation functions. Such that u of x is equal to u1 e psi 1 x plus u2 e psi 2 x e. So, this superscript represents each element. Superscript represents each element. u1e is the value of u at node 1, u2e on each element, and u2e is value of u at node 2 on each element. Okay. At this stage, we do not know what is the nature of psi 1 and psi 2. So, we have to figure out. Now, because it is a linear element, psi 1 can only be a linear function, and because it is a linear element, psi 2 only also can be only a linear function. Okay. So, because psi 1 and psi 2 are linear functions, I can in general write down psi 1 e x as a plus b x, right. It is a linear function, and similarly psi 2 x I can write down as c plus d x. So, what is it that we are doing right now? We are trying to figure out what kind of approximation functions we should have for the eth element, and we do not know the values. So, here A, B, C, D are unknown. So, our aim is to figure out the values of A, B, C, D. Okay. We know that the value of u at first node is u1e, and we know that the value of u at the second node is u2e. It may be, I mean, we do not exactly know, but some general number u1e and u2e. So, in terms of u1e and u2e, we will try to infer, using this information we will try to infer what are the values of these constants a, b, c and d. Okay. So, at x is equal to xa, xa is the first node of the element, u is equal to u1e, right, and we know that u is what? u1 psi 1 xa e plus u2 psi 2 x a e. Agreed? Okay. U is equal to u1e, this is how we have defined u1e, and we have also defined u as ui psi I, summation of that. So, if I have to calculate the value of u at xa, I am using that relation and I am plugging in x is equal to xa here. Agreed? So, this is there. Now, this relation is true for any value of xa. You know, the node could be located here at this location, or it could be, because this is eth element. So, it is valid for all values of xa, and it has to be valid for, it should not depend on values of u1 and u2 also. u1 could be 0, then also this equation should hold true. If u1 is something else, then also this equation has to hold true in all situations. So, this is going to be possible, only possible if the value of psi 1 function at xa is equal to 1 and the value of psi 2 function at xa is equal to 0. Only then this will be possible for all values of u's and all values of, right, because if these two conditions are met, then this will be 1, this will be 1 and this will be 0. So, u1 will be equal to u1, so it will be identically satisfied, right. So, from this what do we get? So, now go back, psi 1 is equal to a plus bx, psi 1 is equal to a plus bx, and what this means is 1 equals, I am going to plug in x is equal to xa in this relation is equal to a plus b times xa. Agreed? And here I have do the same thing for the relation psi 2 c plus dx. So, this is equal to 0 is equal to c plus dx a, right. Then, so this is the condition at x is equal to xa, at x is equal to xb, at x is equal to xb, what is the displacement? u2e, u is equal to u2e, agreed, and this is equal to u1 psi 1, and I am computing this function at xb plus u2 psi 2e, and I am computing function at x b. Again, this is only possible if psi 1, when I compute psi 1 at x b, this is equal to what? 0, and psi 2 when I compute it at location x b, this is 1. So, again this gives me another relation is equal to 0 is equal to a plus b x b, and this gives me 1 equals c plus d x b. Okay. This is equation 1, this is equation 2, this is equation 3, this is equation 4. I have 4 equations and 4 unknowns a, b, c, d. So, I can solve for a, b, c, d, right. I can solve for a, b, c, d, and I can plug them back in these relations, and once I plug them back in relations, I get the mathematical expression for psi 1 and psi 2. Agreed? So, my psi 1 function, so using this method, what I get is psi 1 which depends on x is equal to x b minus x divided by x b minus x a, and my psi 2 function is equal to x minus x a divided by x b minus x a. So, these are my psi 1 and psi 2 function for which element? Eth element. So, E is general, so it does not matter, they are valid, this relation as long as I know x b and x a, the initial coordinate and the final coordinate, I have the psi functions for all elements. Okay. I have the psi function for all elements. So, now that I know this, my u for the eth element, which is a function of x, is equal to u1 e psi 1 e x plus u2 e psi 2 e of x. Okay. So, we will conclude this discussion here, and we will continue this discussion on interpolation functions or approximation functions in the next lecture also. Thanks.